And that's why we start looking at the very special looking matrices, right? I mean, the next slide will have we already take a look at what each one look like: diagonal, tridiagonal, triangular, symmetric, sparse. Sparse we haven't discussed yet. What was the common characteristics of all these four, maybe excepting sparse yet? 1, 2, 3, 4. Answer is right here. Reduced space and time complexity. I mean, comparing to the just normal looking matrix, there seems to be a lot of zeros or empty space if you want to look at it in the matrix. There was one important question someone asked me last class. I will try to go over that. Why there is a zero in here as well, right? We will discuss that. If I forget, you will ask me again when we hit that page. And then the bottom line was we like to store these two-dimensional array looking ones into a one-dimensional array, just like a linear list that we studied the chapter before. Why? Reduce the space complexity. In order to store them into one-dimensional array, what do you need? Maybe I'm speaking too fast. What do you need if you want to store these things into one-dimensional array? You need some kind of formula to follow. What was the two formula that we looked at, the easiest one that we looked at? Well, its answer is right here. Row and major column ordering. Two ways to store this into one-dimensional array. It's a simple formula. If I I'm asking the program that what is the element in position I, or I, comma j, if you want to follow the two-dimensional way. Then using that value of I and j, I put that into a formula, and it will give me a location of a same element into one-dimensional array. So we know how to do this in one-dimensional array, simple as this one. Start always 0 in our questions. 0, 1, 2, 3. Very simple representation, and then we discussed about the space overhead as well later. 3, 4. If this is a 3 by 4 matrix, if I want to ask what is the element of A 1.2, 1, comma 2, exact. Then we already know this is 3 rows. If we follow row major ordering, then what do? You 1 times number of columns plus whatever the offset is. Row major column ordering, row major ordering 하면 어떻게 돼? 이렇게 쭉 썼죠? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. 그죠? If I want to have a value of this part, I just maybe 1 multiplied by number of elements in the first row, and then how much it advanced in the second row. It's a simple formula we've been discussed this way. 여기 이 답인가? 맞잖아 여기. Here. I times C plus J. X, I, comma J is mapped into a position I times C plus J. Very simple formula. Mapping function, they call it as a mapping function. It's a formula that gives you a location of a structure they store the data in. 그죠? I mean, if you do a column major ordering, it's completely opposite. If they store 1, 2, 3, 4, 5, 6, same thing. They will have a slightly different looking formula. 그죠? We know we need the formula, and then we discuss stuff like this. Someone asked me also, what is this? They discuss the space complexity of all this. I mean, they use a value of 4 bytes for having a one array. Okay, think of it as it takes 4 bytes to declare array. It might be easier for you. I mean, that's how much it takes to declare in one array. And it also, in this two-dimensional array explanation, how many arrays do you need in overall? How many arrays do you need? It has 3 rows and 4 columns. So they treat as a single row as a 1 array, 2 array, 3 array, 3 row, okay. But I need to have a pointer that following each row. So I need extra array to have all this. So that's an array of array as well. So this one is array of array, having an array as element. So that's why we said it takes 4 bytes to declare one array. So we declare 4 arrays. 4 times 4, 16. That's how they calculate the value. I would say like that's how much it takes, how much it costs to use this. And in summary textbook would say it's much cheaper than declare just one in this big array. Okay? If you were to think of it that way, it might be easier. Maybe I went there too fast last time. That's why they say 16 bytes is much less than some 100 bytes declaration later. Okay? That's why it's better space complexity solution, lower space complexity solution. What else? We know mapping functions. We all know how to write in column major way, row major way. Which one is better than the others? It's the same thing. I don't care. I don't know. Either way is fine. I don't really care. And that was, if you want to generalize the mapping functions, this was for 2D array. I'm sure many of you look at your books and it goes like they declare a 뭐지? Textbook U1, U2, 그죠? I think for the 3D array representation, they like U1, U2, this is 2, U3. I'm just doing it because I know some of you didn't look at your textbook yet. So if you take this way, we all know this from previous example. This is a function, that formula that we require to map a certain element in the matrix into one-dimensional array. Likewise, for 3D, we go adding another dimension. That's why you multiply U2, U3, offset by I3. So if you do this once, it's pretty much clear. So they also ask you to do a very simple exercise on 7.2, figure 7.2. I mean, 그것도 계산하기 싫으면 just memorize. I don't care. I don't care. 왜 어렵지? I don't understand what part in this chapter is making you difficult. It's quite easy. Especially this slide, they don't even have any implementation details. They don't discuss too much on the time complexity. I understand the previous chapter was a bit confusing. That I understand. This one, no. 이거는 그렇게 어렵지 않아요. I guarantee you after the next chapter, which we will discuss is stack as another data structure, then I'm pretty sure you will get used to the structure of the slide. You will see what's coming in the next few set of slides. 스택, 이 다음 챕터는 스택이라는 데이터 스트럭처를 하는데 이제 봐, 링크 리스트 받고 매트릭스 받고 그 다음 스택까지 보면 그 다음 챕터는 대충 어떤 식으로 슬라이드 순서가 되는지 뻔히 보여요. 그 교과서도 마찬가지고 똑같아. 새로운 데이터 스트럭처, 새로운 데이터 스트럭처에 맞는 오퍼레이션. 그 오퍼레이션을 그 구현하는데 방법. 구현하면 시간이 얼마나 걸리는지 땡. 중간고사 이후로는 새로운 데이터 스트럭처만 보다가 끝까지 가다 끝나요. 12월 달 딱 되면 데이터 스트럭처 몇 개 배웠구나 하고 땡. And then we start looking at the very special cases for like 2D arrays, having a different size of each rows, and then simply they declare into, they translate this array into a maybe pseudocode like C implementations. They use what? They use a for loop, and every time you're doing something inside the loop, they create a new array of different size. They increase the array size 1, 2, 3, 4. This one somewhat look like the matrix that we have looked at. This is like what? I think it was a lower triangular matrix. What's in the above? They don't store it, so I can assume maybe a 0 or -1 if you want to declare whatever it is. So this might be a good representation for lower triangular. Or if you want to flip it, then it's a upper triangular that we briefly looked at. We will look at it anyways. And a bit of preview of the next slide. How much space do I need for this? How many entries do I need in order? So there is n rows, 1 plus 2 plus 3 plus 4. 1 더하기 2 더하기. So how you calculate that? If it's a 10 rows, you adding 1 to 10. How do you calculate that? 얼마야? 1에서 10까지 더하면 55. How do you calculate that? 뭐 n 곱하기 n-1 나누기 2 하면 뭐 아주 국민학교 때 나오는 쉬운 거죠. 초등학교. Yeah. So this was a sample implementation details for, they say, irregular 2D arrays, but just one of the variation of 2D arrays. 여기만 보면 되죠. Every time number of rows is might be 10, 0 to 9, 0 to 10, so 0 to 9 actually. 0 to 9, array 0 equal to new integer array length of, 이거는 1이어야 되는데. This is not right. Yeah, right. 0. Length of I of 0. length가 어디 있니? They store somewhere else. So think of it as integer 1, integer 2, integer 3. Every time they increase this value, forget about this length. In their textbook, they have a length function somewhere, but I don't think I include this in the slide. So it's the same thing. New something, it's declare. That's another way of saying allocating a memory space. When I say new, I say somewhere in the memory, this spot is reserved for me. I can use that memory space. Of course, there are different ways of doing it. I mean, mlock is another way of doing it. Memory allocation functions like that. But those are different implementation details that you can take a look at if you're interested. And then briefly looked at the transpose, addition, multiplication. We all know addition part, but some of you wasn't aware of this transpose function. If you're always confusing, look at the definition. MT transpose Ji is equal to Mij. So they switch the function, switch the position I and j. If the values are equal, that is a transpose of another matrix. So you can do this. I mean, implementation is perhaps easy. I mean, you can go through all the elements in the list. You flip the switch. 어떻게 하면 될까? If your searching function is asking to give you a value of I and j, and then next task is they asking you the value of j and I. But you know the matrix is transposed, so you can just simply return a value of I and j. you don't have to store them in twice. 그죠? 예를 들어 트랜스포즈 매트릭스를 하는데 굳이 매트릭스를 크게 다 가져갈 필요 있어요? 없죠. IJ 물어보는 거랑 JI 물어보는 거랑 똑같으니까 한 줄만 가지고 있다가 JI 물어봤을 때도 IA 주고 IJ 물어봤을 때도 IJ 주고. Addition. You're just simply adding the elements in the same position. I mean, we all know this, and you create a new matrix, something called C, corresponding that location. Multiplication, product of a matrix A and B will create a new matrix size of, if you multiply m by n, m by q, then you will have a new matrix of size m by q. We all know this. If you write that in the formal ways, that's a formula to follow. You can easily translate this formula into a for loops. You can implement this. I mean, if I've given you this, asking you to implement this, that would be a very, very simple question, which I would never ask. 그거는 it's nothing. 그런 거 물어보는 거는 대학에서 맞지 않는 것 같아서 I would never ask you. So just read examples on 7.2. Rows and data, we all know this. And then there was some point to look at, I mean, very easy point. Index R off by 1. So array implementation actually start from location 0. But when we say in the questions, we usually say 1 by 1. 1, comma 1 is first position there. So you need to subtract by 1 at all times. Something to look at. C++ array does not support the matrix operations such as add, transpose, multiply. So I said there are other languages that you can use, right? I don't know how many of you are interested in these areas, but what was the tool that I mentioned last time? I briefly mentioned the tool names, program names that actually can do this. Add, transpose, and multiply. 뭐였지? 무슨 프로그램들이 저런 거 하는 거 있다고 그랬잖아요. MATLAB. Or MATLAB is usually expensive. 학교에 MATLAB 라이센스가 있던가? I forgot. Maybe they do. Or if you want looking for free ones, then Octave is the one to use. Or if you use 내가 적어줄게. 그냥 찾아봐, 재미로. MATLAB. It's like a free version of MATLAB. People like me who doesn't have money to buy MATLAB use this. I think it's open source too. 아마 open source 맞을 겁니다. 아마 아무나 가져다 쓸 수 있게. Or if you're willing to use a Python, look for the libraries that are actually doing a matrix computation in Python. There are libraries that you can use. So you don't need to actually implement all those stuff. If you look at carefully, then there are certain libraries in C that you can use for this matrix operations. So if you encounter a situation of need to manipulate this matrix later in your jobs, do not try to implement them in yourself. 하지 마. 나중에 뭐 취직을 하시든 나중에 유학을 가시든 하셔서 이런 걸 갑자기 해야 될 일이 나오는데 처음부터 짜고 있지 마. 찾으면 다 있어요. So there was not brief review because you guys complained that it's a very long review of what we discussed last class. And let's move to the next slide. Okay, let's quickly catch up to this. Special matrices. Square matrix has the same number of rows and columns. We know m by n matrix, so we're dealing with this. And we see different type of matrices in this way. We have looked at each definitions, but it's always easier to look at actual examples in this way. And there was one question from not just you, many others. If we take a look at, maybe just pick one. 아이고, 어떤 거지? 이거 좋겠다. Lower triangular, C. By the definition of the lower triangular matrix, only this part have the values. This part always 0. But once you look at this example, you see a 0 right here. And I understand you guys start being confused. I completely understand. This is my fault. I forgot to explain it. Why? 여기는 by definition there should be zeros up here, no zeros up there. They don't say it. In the definition there's no zero. So this 0 is actually a data. The value that is actually matters. This one values that doesn't matter. Okay? So you can have a zeros in the lower part as well. But you should treat them as the value that actually matters. Okay? This is one thing maybe I forgot to tell you, and thanks for he's asking me questions, so thanks to him. So don't get confused on that part. I mean, if you look at the definition, they didn't say anything about no zeros in some places. They just simply say zeros in the upper part. So this is correct, for this one, correct lower triangular matrix. And there are other examples having zeros somewhere in there, but you should treat them as a data if that doesn't follow the definition of the whatever matrix that you're dealing with. Okay, that's one thing I just wanted to make sure. Diagonal matrix values only at the diagonal. Tri-diagonal only the difference between I and j is less than 1. They should have a zeros, so the values will be on the diagonals. And lower triangular, the values will be the lower side of the triangular matrix. The matrix upper, the opposite symmetric is the same value and I and j location. So, 뭐라 그랬지? 데칼코마니. If you flip that onto this side. Okay. So again, the bottom line of studying all this special type of matrix is order and we wanted to have an implementation of space time complexity of n. We'd like to use a minimum space as well. Okay, I think I give you example on compression one, right? If you look back on the earlier this year's Introduction to Computer Science, when we're discussing the images. Images are, the colors are represented in numbers. So images are matrix, right? That's one thing that we discussed. 이미지가 뭐야? 이미지 파일이 다 매트릭스잖아. 색깔을 숫자로 다 표현해서, 그죠? 그래서 0으로 돼 있으면 허옇게 나오고, 뭐 10으로 돼 있으면 뭐 예를 들어 검게 나오고, 그걸로 이렇게 모자이크처럼 그림이 하나가 완성이 돼. 픽셀이 하나가 숫자 하나잖아. 우리 했었잖아요. So if you want to think about that way, I mean, if you want to store all those numbers of that images, then it will be really big files. That's why some of the movie files of quality of more DVD or what's the better Blu-ray. It's sometimes movie files, a couple of gigabytes. So, and then you do a codec compression. 뭐 그런 거 하잖아. 애플 있는 사람. Who's using Apple device? Who's watching movies from your Apple device, iOS? 아이패드 쓰는 사람 없어? iPhone. No one watches drama on iPhone? In order to convert the video format into iOS formats, then you need to spend some time. 아무도 안 해? 비디오 안 봐? 드라마 안 봐? 인코딩, 그래, 인코딩 얘기하지. That's what they're doing. I mean, they take the set of matrices, doing an encoding. They actually changing a numbers into a smaller pixels. So when they're doing that, maybe they wanted to have a minimum space as possible. I don't know. On the side, the encoding takes a long time, 그죠? Sometimes maybe 20 to 30 minutes if you want to encode a large file into a smaller codec. Because it's all matrix operations, that's why it's taking so long. 뭐 곱하기도 하고 더하기도 하면서 줄이는 거죠. 너는 드라마도 안 보는구나. That's one of the reasons that I don't use the iPhones anymore, because it's hard to watch dramas. I don't want to do encoding every single time. Wonderful Android phones that they can let me play any format I want. So if you're thinking that this matrix seems to be, I mean, it's garbage, but if you actually take a look at the actual examples that you use every day, hopefully it's close to you. Okay. And distance matrix we briefly looked at is from each city to any other cities in that map, you can find out the actual distance between two. Of course, the diagonal is 0 because you're pointing to yourself. So that's a typical example of distance matrices that we can use. This one I already kind of discussed. If you just simply use a normal n by n matrix, that's how much space that you need for n square n, and times if it's an integer array, integer is size of 4 bytes. So n times 4, that's how much space it requires. In better ways, you can do, if you do a, not a good example, but you can do a n elements max if you're dealing with a diagonal matrix. If you do a diagonal matrix, you only need to store this. So that's n. If this is also integer matrix, 4 bytes, n times 4, so it's much less. N times less than the naive way of implementing diagonal matrix. Naive way is 그냥 대충 하는 방법. Naive way. So you see a space complexity of these two approaches for the special diagonal matrices. C program 7.84 class diagonal matrix. 뭐겠어? Much simpler than the typical matrix that you look for. Tridiagonal. Non-zero elements lies on the 3 diagonals. 1, 2, 3. Without even looking at this, what's the total number of elements that I need to store? 이렇게 돼 있으면. We're discussing square matrix n by n, so I need to store, 그죠? n. This one is, well, 에이 구차. You do the math. 3n minus 2. You just add them all. That's how much space that I require for this. It's another way of comparing a space requirement for different implementations. We're not discussing the time complexity at this point. 그렇죠? 이거 할 필요 없지? 이거 뭐겠어? Row major ordering. 이거 어떻게? 뭐 이거겠지? In the same order. Column way is 2, 3, 1, 1, 5, 3, 2, 9, 7, 0. This one I need to store 0 because this is data. So diagonal, I don't care. I mean, there are other ways of storing the information. If we look at it, they actually store in the diagonal major ordering in 359. So they store the underneath diagonal 350, 2120, 137. If I ask you to diagonal major ordering for formulas, can you do it? It's not so much different from row and column major. So take a look at it for more, and other examples keep coming up. Tridiagonal. Mapping by diagonals beginning with the lowest. This just the one we simply looked at. Switch I minus j, case 1, case 0, case minus 1. What do you do if you do this? 이거 방금 본 diagonal way, diagonal mapping way. 이거 뭐야? Switch I-J. What's this command for? 뭐지? 이거 뭐 보면 뻔한데. Switch I-J. It's like an if statement. The value of I-J is 1, do this. Value of I-J is 0, do this. -1, do this. Case 1, lower diagonal, that's why they -2. Main diagonal, this is how they calculate the main diagonal. This is upper diagonal. So 3 cases. I mean, those are the only 3 cases they have to look for, right? Only 3 rows will have the tri-diagonal matrix elements in it. So switch, for programming perspective, switch is another way of doing stuff. Some people prefer switch because they can write it down something like this. If none of the conditions match, do something. It's like an else statement in the if. fault 같은 거, exception error 같은 거 잡기도 좀 편하고 하니까. Switch, it's another way of practicing your style of coding. This one I already mentioned. Triangular matrix is either upper or lower, it doesn't really matter. How do we calculate how many elements do I need in that matrix? Well, 1 plus 2 plus 3 plus 4 plus n. That's I mentioned last slide. So n times n plus 1, not n minus 1, n times n plus, 미쳤구나. N plus n, n times n plus 1 divided by 2 is the elements of the non-zero regions. I mean, still the upper bound of this implementation is n square. upper bound은 n square죠, 그죠? n times n. That is upper bound if it's worst case. But this is the actual minimum number that we can have in this implementation. So it's good to have these type of special matrices. I mean, you can remove the unnecessary space and still can answer the questions asked to the matrix operations. And plus, it will be much easier to operate. ADTs, in terms of time complexity of ADTs on top of this matrix, hopefully will be much slower, much faster than the naive way of implementing the matrices. 뭐 하러 봐? Row major ordering. 2, 5, 1, 0, 3, 1, 0. 아이고, 또 나 잘못했다. I shouldn't be including this 0. 2, 5, 1, 0, 0, 3, 1, 4, 2, 7, 0. Be careful on that part. Lower triangular matrices, I mean, it's pretty much straightforward after this point. Lij 0 if I is less than j, otherwise that's what it requires for that. That's a function for that lower triangular matrix ones. For the upper triangular matrix, I say question mark, but if you flip an I and j on this lower triangular, it's pretty much the same. 여기서 ij 포지션만 바꿔주면 it's the same formula that you can use. Try to read the textbook for this part. It's not that difficult. Symmetric matrix, I already mentioned as well. I mean, it's a flipping index values of 2 positions, so you just need to simply store a one-way I and j. Then you will be able to answer back j and I because it's a flip over it. N by n matrix can be represented using 1D array size of n plus 1 by 2 by storing either lower part or upper triangular of the matrix. So it will be the same space complexity of the lower and upper triangular matrix, right? I just simply need to store it in this side or this side. Using one of the methods for a triangular matrix, the elements that are not explicitly stored may be computed from those that are stored. That simply means I know the exact opposite side from a one side because it's a symmetric matrix. This one we didn't discuss that much yet. Sparse. So what is a sparse in vocabulary, I guess? Sparse. It's very rare. It's some values in here. It's a bit of random like, and a lot of locations in the matrix are value of 0. So it's sparse. 되게 퍼져 있는 거, sparse matrix. Sparse matrix. In case of sparse matrix, because values are spread all over the place of the matrix, is it a good idea to store all the values into n by n? Just naive way of implementing matrix data structure. 어떻게 하는 게 좋을까? What do you suggest if I want to reduce the space complexity of this sparse matrix? 그냥 뭔 방법이 좋을까? Yeah. If you want to store the values that is not 0, then what do you need? You probably need a location of the values that is not 0. It means you have to store a location information of the values that you actually care. Hopefully that might be a less space than that we store the everything in it. Now, this is very nice, giving you everything. The typical assignment questions like I probably give you, this is sparse matrix, implement that in data structure with the minimizing space requirement. They don't tell you what to do. They don't tell you what to do. 그 일반적으로 어사이먼트 많이 좀 더 어렵게 한다면 그냥 스파르스 매트릭스 데피니션만 딱 주고 스파르스 매트릭스를 구현해라. 단 대신에 메모리를 최대한 적게 쓰면서. 답을 알면 굉장히 쉬운, 답을 모르면 여러 가지로 머리를 굴리기 시작해요. 로우 메이저로 갔다가 막 나중에 황당한 경우는 랜덤 하는 애들도 있어요. 그냥 막 계속 찍어. 발류가 나올 때까지, 0이 아닌 발류가 나올 때까지. 재수 좋으면 그것도 맞을 수 있겠죠. 그죠? 정말 재수가 좋아서. 아니면 스파르스 매트릭스가 어떤 패턴을 가지고 있든지 2개 걸러서 하나가 나오고 뭐 3개 걸러서 하나 나오고 이런 게 계속 연속되는 패턴이 있으면 재수자수 딱 걸리면 딱 되겠죠. 근데 그렇지 않고 스파르스 매트릭스 일반적으로 얘기할 때는 그냥 어떤 패턴을 특별하게 찾을 수 없이 퍼져 있는 경우 이렇게 얘기하면 됩니다. 여기서 스파르스 매트릭스 자꾸 이미지 얘기를 해서 그런데 이미지 얘기할 때 스파르스 매트릭스 하면 뭐가 나올까? 예를 들면 이렇게 보면 돼. 사람이 걸어가는 비디오 파일이 있잖아. 이렇게 걸어가면 사실 동영상이라는 게 그림이 계속 연속적으로 붙어 나오는 거 아니야? 우리 어렸을 때 장난치듯이 이렇게 책에다 쫙 그려 쓱 하면. 그래서 첫 번째 이런 화면과 그 다음 화면이 매트릭스로 놓고 보면 매트릭스가 상당히 비슷해. 크게 변하지 않아요. 내 발 움직이는 데만 숫자가 변했으니까. 그죠? 그러다가 갑자기 그렇게 패턴이 있는 게 쭉 나오다가 갑자기 이런 생뚱맞은자가 쭉 나오면 그냥 까만 화면 나왔다가 다시 없어져요. 뭐 끊어지는 화면? 이렇게 볼 수도 있겠죠. 그렇게 이해하면 좀 나을까 모르겠어요. Anyway, try to picture that in your brain, and this is matrix. I mean, it seems to be just number operation, but these things are related to those maybe image processing later. Okay, when you do a 3D projection video, it's also manipulating this 2D matrix into 3D matrix. 그때 한번 얘기하지 않았나? 3D 영화 같은 거 나올 때 안경 벗고 보면 이렇게 약간 겹치게 보이지? 이렇게 뭐가 이렇게 붕 떠서 보이잖아. 그만큼 2D 화면을 3D 축을 하나 더 추가해 주니까 그만큼 값이 더 들어가야 되겠죠. 3D 매트릭스. 그래서 이렇게 눈 뜨고 보면 이렇게 좀 이렇게 겹쳐 보이는 게 이렇게 나오는 게 다른 축이 하나 더 들어가서 그런 거예요. 3D 영화 보면 크잖아. 왜 우리 지금 매트릭스 얘기하는 그거지? 3D 뭐 곱하기 더하기 하려면 더 오래 걸리잖아요. 그죠? 3D 매트릭스 곱하기 하면 타임 컴플렉스가 얼마야? The worst case, upper bound. What is the upper bound of a 3D matrix multiplication? N은 4제곱, n to the 3. 그죠? It will be much more expensive. Imagine that that thing is doing by your TVs. TV have a very low CPUs and not good memory. That's why some smart TVs are slow when you try to watch a 3D. Okay, matrix sparse if many of its elements are 0. Matrix that is not sparse is dense. Opposite of a sparse matrix, we call that as a dense matrix. Things are concentrated in certain portion of a certain location of a matrix. Boundary is not precisely defined. Boundary is not precisely defined, exactly say sparse. I cannot find out the pattern, maybe. I cannot draw a line within the matrix, maybe upper this bound, no values there. It's hard to say in those matrices. Boundary is not precisely defined. Diagonal, tri-diagonal matrices are sparse. We classify triangular matrix as a dense. These two, it's okay. I don't care too much. Okay. Two possible representations, array or linked list, just like any other matrix. Thing is this is my 4x8 sparse matrix. The values that I care is maybe 2, 1, 6, 7, 3, 4, 5, 8 or 9, 8, 4, 5, those values. But there seems I cannot find the pattern because my IQ is low. I cannot see any patterns in it. If you see a pattern here, you're smart. IQ 테스트가 저런 거 많이 하지, 그죠? So I just simply store a value and location of that thing. So row 1, column 4. Row 1, column 4. Value is 2. So I guess I need much more than 1D array, but I store this information as well. Index information. Row 1, 하나, 둘, 셋, 넷, 다, 여, 일곱. Column 7. Value is 1. Its representation, it should be that way. I mean, it's one of the suggestions that you can do. Non-zero elements may map into a 1D array in row major column, a row major order. To reconstruct the matrix structures, need a record of a row and column of each non-zero comes from, where it comes from. So simply means I might need a separate array to store this a row number and column number in order to reconstruct. 다시 만들려면 need to get it back from this. So that's one of the array representation of a sparse matrix. Just think of it as this one. It's a sparse matrix. They declare another class that having a row, column value as well as the data value itself. They include as a one of them. So they simply do this way of doing it. See program 7.13 to 7.17 for class definitions and methods of sparse matrix. Again, this is not the only solution. This is not the only solution. This is one of the suggestions they can do. I mean, you could choose to do the other ways. I mean, if you do this in C, maybe you don't even need this template, so whatever. You just simply need a structure. Doesn't really matter. So just take a look at for your references. Link representation of sparse matrix. 이건 뭐 what can you see from this diagram here? What can you see? Maybe as I reading the value of the data, I create how many rows first, each row, as I see a value, I store the location of the values and the value itself. I keep adding a new node in it as I see one. So it's one of the way of doing it. I mean, if you don't want to do this in array way of it. 아까처럼 뭐 예를 들어 002 000, I don't care. As soon as I see 2, data is 2, location column value, row 1, column 뭐지? 4. Go it, do, and when you see a 1, value is 1, row, column, whatever value that comes. Of course, I need to have a link pointer. Sorry, link. To be more exact. Field, I don't care here. You can have a separate field here. So it's a linked list way of doing it. Create new node, add into a new position this way. This might need another pointer here as well. If you wish. I mean, it's any type of design is fine as well. Any type of design is fine as well. If I do that, I probably don't do all this. I just simply do it one way. And I keep changing the row. This is end of row 1. Next value I see, row 2, column, whatever value it is. Maybe I do a one simple array, like that. Which way is fine? Either way is fine, I don't care. It's one of the suggestions for you to take a look at it. Maybe what I draw here is slightly different from what they actually try to explain in the textbook, but it doesn't really matter. It's up to you. It's up to you. So do take a look at how they did it in the textbook. A shortcoming of 1D array of a sparse matrix is that we need to know number of non-zero elements in each of the sparse matrix when the array is created. Someone say we need some type of prior knowledge of a structure of the matrix itself. But in terms of linked list way of implementing this, I don't need to know any more information in the beginning, at the beginning. So I just, as I see it, I can continue this way. Linked list representation can overcome the shortcomings. Just add new values as it proceeds. See program 7.18 for linked list representation of a sparse matrix. Read chapter 7. What do I mean by read chapter 7? Again, those programs or the example diagrams that I say in the slide, just do take a look at those things first. If you don't have enough time, then you don't need to read chapter 7 from the beginning. Just do take a look at those examples. Matrix, chapter 7. Chapter 7. So next chapter is chapter 8. 그죠? Okay, read chapter 7. So I'm gonna call your attendance now. And I will collect your assignment. Assignment 1 is due today, 그죠? 성원, 부탁합니다. 두 분. 할 수 있으면. So you will hand your assignment to these two. 숙제 이 두 분한테 내주시면 고맙겠어요. 앞에 출석 부르고 나서. 오케이? 출석 부릅시다.